So today we're learning about planes. So planes are anything like this sheet of paper here. So a flat piece of area defines a plane. We'll actually start with a line to figure out what a plane is. So here's a line, x plus 2y minus 6 equals 0. So I found its x-intercept over here. Its x-intercept will happen at positive 6. And its y-intercept over here, it's going to happen when x equals 0, so that's going to be at positive 3 here. And then I've got my line in my 3D space here. You can see that this line is sitting on the floor, and z is coming up from there. What if I instead looked at this crazy looking thing here? It looks almost exactly the same as my line. X plus 2y plus 0z minus 6 equals 0 here. So why did I add in this 0z term? What I want to do with this is turn my line into a plane. And so by including the concept of z in my line, then I allow this line to stretch out over 3D space. Because there's a 0 specifically in front of the z, that means that z could be anything and still be described by this equation. Z could be 0, like it is right now for my line, but z could also be 2. And that would be a similar line kind of up here, parallel to the line that I have. Maybe z could be 3, a little bit higher. What I'm creating is a wall here that rises up above that line. If I were to do it in 3D, my plane is literally sticking up off of the ground like that. So that's kind of what a plane is. You'll notice it looks a lot like the standard form equation of a line. That's because this is the standard form or scalar equation of a plane right here. So if we were to describe the scalar equation of a plane, it goes just like the standard form or scalar equation of a line. Ax plus by plus cz. So it's crucial to have a three-dimensional plane. You can't talk about a plane in 2D. There's just nothing there. You need to have 3 dimensions to have a plane. And just like a line, it's got a constant d at the end. And that all adds up to 0. So it looks very much like our scalar equation of a line, but it's in 3 dimensions. It's like taking a line, spreading it out over the 3rd dimension. Let's use that equation to find out maybe if a certain point is on the plane. So what do I mean by a point on the plane? I mean that if the plane is maybe oriented like this in space, the point that we're looking at can be found somewhere physically on the plane. So that would be point A right there. So maybe the plane's oriented in space, point A is on the plane. Point B maybe is someplace over here. That would be a point off the plane. It's not physically on this space. So our question here is looking at this plane, negative 3x plus 4y minus z minus 2 equals 0, is the point 1, 2, 3 on that plane. To check, I could check just the same way I would check if a point is on a line. So I'm going to take my point and plug it into my plane equation. So I'll do negative 3 times the x component, which is 1, plus 4 times the y component, which is 2, minus 3 for z, minus 2, equals 0. Is that true? Let's check. Negative 3 plus 8 minus 3 minus 2. That is indeed 0. Because that all adds up to 0, we can say that, therefore, point A is in the plane itself. All right, now more cool things that we can do with planes is actually create vectors in the plane. So what do I mean by a vector in the plane? Well, that would look something like this. Here's a vector, or maybe here's another vector. Those vectors you can see are physically on the plane themselves. They're parallel to the plane, they point along with it. A vector that's not in the plane would be maybe something like this, coming out and poking through the plane. That's not in this plane. All right, so we're going to find vectors that are in our plane here, x minus 2y plus z plus 3, just another plane. To find a vector, I always can get a vector out of finding points. So let's see if point A is a good point, if this is a point on the plane. We'll just check here. Is point A on the plane or in the plane? Is point A in the plane? let's see, so we'll plug in the x is 5 minus 2 times the 3 plus the z, which is negative 2, plus 3. Looks like this is indeed in the plane. So point A is in the plane. Now we need to make another point. We can make any point we want that's in the plane. So when I start making a point, sometimes I just pick my favorite number for x. 1 is a really easy one, so I'll pick that first. And then I pick any number I want for y. Let's do 1 again. And then I just figure out what z has to be in order for point B to be in the plane. So if point B is going to be in the plane, x minus 2 times y plus whatever z is, plus 3, has to add up to 0. So let's just solve for z and see what we get. I have z minus 2 plus 3 plus 2 is equal to 0. So z must equal negative 2 here. So that'll be my last coordinate of this point in the plane. So now I found 2 points that are in this plane. I could find millions of points that are in this plane. There's literally an infinite number of them. But 2 is all I need to make a vector. A vector in the plane, I could call it vector AB. It's going to point from A to B, and I can find it just by taking point B and subtracting point A. So what I'll have here is B, so 1, 1, negative 2, minus A. Oh, I'm writing these as vectors. It doesn't really make a difference. I guess I should probably write them as points, though, because they really are points. Okay, there we go. Let's do our B minus A. So I get negative 4. Now, this is definitely a vector here. Once we do B minus A, we literally have the vector that points from A to B. So 1 minus 5 is negative 4. Negative 2, when I do 1 minus 3, negative 2 minus negative 2, that's actually just 0 there. So what we found here is another vector, AB, that lies inside this plane. So just a reminder, that's like an arrow here that is in the plane itself, not poking through it, but parallel to the plane.